How is that? Is that working?
Okay, yes. So please
Great.
go ahead.
Thank you. Well, thank you for inviting me to present to the Security Working Group. What we're going to be speaking about today is the implications or considerations for DDoS resilience and protection for the design and development of advanced networks. And what we're going to do is I'm going to present some of my experiences during the past year working with DDoS and helping sometimes members of APAN and also members of research and education networks in the rest of the world protect their networks against the evolving threat of DDoS. So in general, cyber threats of all kinds are increasingly sophisticated each year. DDoS attacks are rising in volume, the size of the attacks, complexity of the attacks, and also the frequency of the attacks. Last year in 2020, a couple of the records were the largest attack that was discussed was around 2.3 terabits per second. And in terms of a rate-based attack, the largest attack was around 809 million packets per second. So DDoS attacks have been around for pretty much the last 20 years. At Corero, my experience spans the last decade, since around 2011. And as I mentioned today, we're going to be speaking about the experiences of the most recent year, 2020. So some of the lessons we learned from last year. So here's the agenda of topics I'd like to cover today. We'll talk about the general evolution of DDoS, but then also look at the services that are being leveraged, updated information on those services that are used for amplification. We'll talk about new styles of attack designed to evade legacy protection mechanisms. We'll talk about the growth of multi-vector attacks, typical attack durations measured from the hundreds of thousands of attacks that we monitor and analyze, and then also some trends related to the rise of ransom DDoS and also DDoS botnets. So in terms of the evolution of DDoS, beyond just higher bandwidth attacks and higher rate attacks, and we routinely see attacks over 100 gigabits per second and with packet rates of greater than 100 million packets per second. One of the factors we're following is the rise in the use of botnets for DDoS. This is also driven by the Internet of Things, IoT devices, many of which have very weak or non-existent security or are not able to be patched or updated once they're deployed on the network. Therefore, if they do contain a vulnerability, they can continue to be a problem for years after they were sold or initially installed. We also see the use of multi-vector attacks continuing to grow each year. We'll speak about that. There are still a lot of dark web booter or stressor services, DDoS for hire services that mean attackers or malicious actors can launch attacks without really having any technical experience. They just need some internet currency in order to click a few buttons and order an attack. And then another interesting development is attacks on what I've called the internet supply chain. So instead of just attacking the victim, the attackers are proceduralizing how to attack the service provider that is hosting the victim, or maybe the DNS services that the victim requires to operate, maybe also attacking the victim's reputation, getting them blacklisted, and launching broader attacks to the address blocks that contain the victim's address. So these are all escalations of the attack surface related to trying to attack a particular IP-based service. So IP services, or the services of the internet, have always been vulnerable to an exploit called DDoS amplification. Very simply, sending a small message to one of these services can result in a very large response. And this is harnessed by DDoS attackers to amplify their attack traffic to levels that can cause significant congestion or outage. Some of those attack vectors are old. They've been around for years. The colored bar chart shows our analysis over the last few years of the typical composition of the different vectors being used, amplification vectors that are being used. Some, as you can see, have been there for years. The blue streaks or the green streaks have been present since 2017, sometimes before that, all the way through to last year. Other amplification vectors are relatively new. The chart below shows how open VPN servers were being used last year in increasing numbers to cause DDoS amplification or be leveraged for DDoS amplification. And we'll speak about that in a little more detail. It's also important to point out that if we don't design our networks and services correctly, the attackers will find many more opportunities for amplification. And while 5 years or 10 years ago, they may have used the fundamental operation of a protocol to amplify an attack, now with methodical scans and analysis of internet-based services and implementations of internet-based services, they find precise weaknesses or opportunities for amplification that may be the result of poor configuration or a protocol design flaw in the implementer's software. And they will now have the tools to find those and leverage those for DDoS attacks. So we'll speak about ensuring those kind of services aren't present on your network. So let's speak about a few of the new services that were leveraged last year. There was a group of 4 services that happened to be featured in an FBI warning about DDoS amplification vectors: the constrained application protocol, web services, dynamic discovery, the Apple remote management service, and then an automation app called Jenkins. All of these services were increasingly leveraged for DDoS amplification during 2020. So in this chart, we can see how the CoAP protocol went from almost no presence in terms of DDoS attack vectors. And then during 2020, it became known or became leveraged by some of the booter stressor DDoS attack services, and then was used a lot during the year as a component of multi-vector attacks. In terms of OpenVPN, many users are leveraging the OpenVPN protocol and client server model, particularly with COVID-19 and the work from home. We've seen about 10,000 OpenVPN servers added every month during 2020. And using a tool like Shodan suggests that there are about 800,000 easily addressable OpenVPN servers on the internet at large. The way that the attackers leveraged OpenVPN servers was interesting. The protocol for establishing a client server session with OpenVPN, it involves a UDP-based handshake, but some implementations of OpenVPN, in particular one open source implementation, happen to have a rather naive retry mechanism, such that if you sent it a session open sequence and it responded to that sequence and it didn't receive the follow-up reply, then it would retry sending the server response. And it didn't just retry once, it would retry every half second for the next 30 seconds. So that means it would retry 60 times. Now, a DDoS attacker realizes that that particularly helpful application is now a vector for DDoS amplification. And we saw OpenVPN used in that way in many attacks during 2020. So you can see that it's not the fundamental protocol of the service that's being leveraged. It's a particular flawed or naive implementation that exposes its use as a DDoS amplification vector. The same can be said too of the connectionless LDAP protocol. This was never really intended to be used on the internet at large, but due to what you might consider poor default configuration, many Microsoft servers by default expose this service to the internet facing ports, and therefore due to the large number of those servers, it becomes a great vector for DDoS amplification. Another more recent DDoS amplification vector that was in the news was related to Citrix products and their implementation of DTLS. And it turns out that in their progressive implementation of DTLS 1.2 and 1.3, there was what you might think of as a missing handshake that would allow a spoofed request for a connection to obtain a larger response. And the protocol actually has built into it a verification handshake, but it was not followed strictly in this implementation. So out of all of the DTLS implementations and uses on the internet, the attackers found the amplification factor available from the Citrix implementation, a particular Citrix implementation. And because there were tens of thousands of those servers visible on the internet, they were able to leverage that to launch attacks. This particular attack also gathered attention because the attacked server, the Citrix implementations that were being leveraged for amplification, would be generating a lot of attack traffic back to the internet and often would overload the outbound links from those systems, causing an outage, a local outage of that service, even though it wasn't the victim of the attack, it was just collateral damage. So all of these examples add up to hundreds of thousands, potentially millions of internet accessible amplifiers out there in the internet. So this is a problem. DDoS amplification is a problem we're going to have to live with for many years. It's not going to be solved anytime soon. And it's important in the network design to realize that these communities of servers and services could be used maliciously at any time. There's a great protocol or best practices, I should say, called BCP38 that's intended to help limit spoofing. Unfortunately, while it's very good at preventing spoofing from a BCP38 controlled network, these attacks that we're describing here don't really get solved or constrained by BCP38. That's because the attacker simply needs to find some network somewhere on the internet that does allow spoofing, and from there they can launch these source packets that will then be amplified by these servers, and these servers originate the traffic with genuine IP addresses. So BCP38 does not prevent a DTLS server or an OpenVPN server or even a CLDAP server from launching the amplified responses. If we look at CLDAP, sometimes it takes years for it to really mature in terms of its use. Corero, we issued an advisory back in 2016, almost 5 years ago, that this vector was going to be a problem, and we forecast, because many of the servers running this service were well connected in terms of bandwidth to the internet, that it could be used to launch a terabit attack. In fact, we saw this February, Amazon or AWS announced that they had been the victim of a 2.3 terabit attack using the connectionless LDAP amplification vector that, as you see from this chart, has been known about and been widely communicated for the last 5 years, yet still there were enough instances available to launch a multi-terabit attack in February of 2020. Another factor in terms of how DDoS is evolving is described here, where we're seeing increasing number of DDoS attacks targeting multiple IP addresses. So for many, many years, a DDoS attack would be the result of traffic being sent to a single IP address, the victim IP address. And many DDoS protection mechanisms were based on blocking or blackholing, scrubbing that single IP. So what we're seeing, sometimes we believe in response to those legacy protection mechanisms, but also as a result of more sophisticated attackers, we are seeing DDoS attacks where IP addresses will be used sequentially. So you'll have the full power of the attack against IP address 1, then the full power of attack against IP address 2, and then the full power of the attack against IP address 3, all within the network that contains the target, the victim target. A different kind of attack, sometimes we believe referenced as a spread spectrum attack, will take that volume of attack but spread it over multiple IP addresses at once within the target address space. So you'll get some packets to IP address 1, some packets to IP address 2, some packets to IP address 3, all at the same time, diluting the traffic level to any single IP address, but obviously all of those packets end up in many cases flowing over the same connection. And then a third characteristic is a pulsed DDoS attack. Here we see a burst of activity against one IP address and then quiet, and then a recurring periodic burst again and then quiet. There are many theories about the motivation for this kind of attack. One of them certainly is that it can be harder to detect these short, sharp attacks, even though they can cause recurring outages when they're present. But another one that we believe has been demonstrated by forensic analysis is this is a result of the DDoS for hire services multiplexing or sharing their attack weapon. The attack weapons we described in terms of amplified DDoS, there's only one instance of those in the internet at large, and they're shared effectively in a non-democratic way by all of the malicious actors who want to leverage those amplifiers. So with this, we often believe that somebody else is being attacked during these quiet periods using that same DDoS botnet or DDoS amplification list. It's just that you don't see it if you're observing this from the point of view of victim IP address 1. So all of these new techniques present new detection and mitigation challenges in 2021 for advanced networks. So just a sound and video check. Are the slides still advancing okay, and can you hear me clearly?
Yep, everything's good.
Great, thank you. Another aspect is the rise in multi-vector attacks. So we find from our analysis that last year, more than 20% of DDoS attacks contain more than one vector. That means the attackers are mixing and aggregating the different attack mechanisms during one attack. This makes the attack larger in many cases, but it also makes the attacks more dynamic and makes the detection and mitigation of an attack into a multi-bodied problem, as it were. So, for example, this is a single DDoS attack we observed against target. This particular one was 18 minutes long. It included more than 8 different vectors that you can see represented by the colors, and you can see that the intensity of the attack varied greatly as those different vectors were bought online or offline, sometimes for only a minute at a time. The period of the data points on this chart is about 1 minute separation per change in peak. So this makes it difficult not only to correctly detect what's happening at any point in time, but it also makes it difficult to make decisions about how to mitigate an attack when 1 minute it's coming into your network at 1 gigabit per second level, and then you might make a decision based on the level of the attack this minute. 2 minutes later, it could be 10 times the size, only to drop to half the size again a few minutes later. So particularly when you're redirecting traffic to scrubbing resources, these are very challenging attacks to mitigate and decide whether they're going to cause congestion and outage or whether they're just going to be manageable by the defense techniques that you're using. Another factor to consider is attack duration. 84% of the attacks we monitored last year were less than 10 minutes. So we're seeing a lot of directed, sharp, short, but high volume attacks being used by the malicious attackers. Multivector components, as we mentioned, are increasingly present. And what this is really conspiring to create is a situation where you have to have an automated solution for DDoS. 5 years ago, a DDoS attack may have arrived at your network and you could afford to have humans look at some screens, do some analysis, and select a mitigation a technique, a black hole, a scrubbing, a cleaning, a redirect, a filtering action. We're seeing increasingly now the level of frequency of attacks, the component vectors, and the variability, sophistication, means you have to adopt automated solutions if you want to prevent these attacks from penetrating your network and services. So given that a large number of attacks are less than 10 minutes, it means you can't use systems, many of which were used for years, that might take minutes or even require a human operator to enter mitigation. What you need is an automated system that can go from detect to mitigate in seconds, not minutes, if you want to be able to block the majority of the DDoS attacks that might arrive at your network. And in fact, one of the APAN members has deployed this kind of technology from Corero, where here we're showing the reaction of the system on 1 second bars. So every one of these bars is a second, and the attack starts here, and within 10 seconds, the attack's already been detected, analyzed, and the mitigation has been communicated back out to the network, configuring the appropriate actions in order to successfully mitigate the attack. And sometimes this happens to not just one attack, but multiple attacks, more than 10 or 20 attacks or components of attacks at the same time. So this is feasible at a large scale, at terabit scale now, with the right kind of automated DDoS defense mechanisms that leverage the capabilities of your network infrastructure. Another factor we saw in 2020 was the rise of ransom DDoS. So we for many years have heard about, ransoms, pay money or else we will attack you. But in 2020, we saw a much more determined and capable set of ransom attacks, typically based on our experience with customers. It would be an email warning or maybe a warning attack followed by an email demanding cryptocurrency ransom with a threat of a larger takeout attack if the ransom wasn't paid. And we've actually seen these larger attacks then occur. So this wasn't a bluff. There really was, a blitz or an attack behind it. And then following that, there might be repeated ransom demands, even if using technology like we just described, the customer was able to defend themselves against the takeout attack. So this is widespread, and some customers, some victims are paying, which of course feeds the business case, if you were, for the criminals involved here. The last insight I wanted to present was the rise of DDoS botnets. So we all hear about botnets for a variety of reasons, but with DDoS botnets, in the design of your network, you can really help prevent DDoS botnets taking hold of your network by making sure any unnecessary ports or services aren't exposed. So you're minimizing your attack surface. You can monitor or pay attention to the outbound activity of your network. And you can use threat intel to block well-known command and control or C2 networks that might be trying to use your network resources. But increasingly, we're seeing that network operators have to have mitigation capability for outbound attacks. So this is not when you're being attacked by a DDoS bot, it's when you're unwittingly hosting a DDoS bot. So, a normal DDoS attack comes in from the internet to your network in search of the victim IP address and causes congestion and problems on the network. However, what's happening with DDoS botnets is that the normal traffic that would be leaving your network is infiltrated or polluted by traffic from DDoS bots that are present on your network. And it's increasingly difficult to prevent DDoS bots from finding a place to hide or exist on your network. That means the bot herding from a bot master to launch those attacks is becoming more and more sophisticated and harder to prevent. We've seen examples of automated bot herding, that is searching for the creation of bots on your network or the networks and the subscribers of your networks. We've seen botnet growth rates, not just of 10,000 bots in a day, but we actually observed data that suggests more than 100,000 bots can be recruited in a day on particular networks. And while we don't have the evidence, it's very likely that some vectors can recruit 1 million bots in a day. And then when they're used to launch outbound attacks, they can have all sorts of unwanted impacts on your network. First of all, there's the unwanted traffic, the impairment of the service levels that you're offering your customers of your network. There's the reputation impact, because your IP address space is being used to originate attacks, and you'll find references like these showing up for IP address space that belongs to you or your customers. Collateral damage, noisy neighbor. This often causes congestion and infrastructure outages, increasingly so in 2020. And of course, bots are an enabler for a broader set of cybersecurity issues. We had one botnet incident, in fact, in 2020, last year, where this caused an outage on a major service provider network. The botnet had been dormant for a long time, but then the botmaster used it to create an attack. In fact, it was an attack against a Russian-based service, but the attacks were very specific. They were 1 minute spikes. So the attack only appeared for 1 minute every 10 minutes, every 30 minutes, but to a different IP address. So this was an attack that was not obvious at first to the operator, but was causing those spikes were causing intermittent outages for communication from that network to the internet at large. So a very problematic botnet infestation that resulted in collateral damage outage for this network, even though they weren't the victim of the attack, they were just being used to attack others. So that's the end of the review of some new things we learned last year. In terms of recommendations for the design and deployment of your network, obviously it helps to understand what is going on in the DDoS space at the current time. We really recommend pursuing real-time protection. So work towards the automated responses and rapid techniques that allow you to do rapid detection and mitigation. They don't have to do it for every attack, but it's possible to get solutions that will take care of the vast majority of attacks for you, meaning that 99% of the time your network is protected, and that leaves you with a focused opportunity when there's an unknown or new attack to go pursue it. And then also increasingly we're seeing people consider hybrid DDoS protection, where you combine protection on your own network with the ability to call for protection in the cloud as well. So I hope that's been helpful and given you an update on some of the things that are happening in the DDoS world, and how you can take that into account when you're designing or configuring the next iteration of obviously the very large networks that you are responsible for or participate in. Thank you very much.